hydraulic flow of the groundwater. To explain the flow pattern of the groundwater, we have to uh, to to use the three equations. The first equation is a quantity equation, boundary equation, and Darcy law. And we apply the differential equation to explain the two different types of flow. We call the steady flow. It means that it doesn't change with time, and unsteady flow it means it change with time. Okay, and let's start from derivation of the groundwater flow equation based on the for confined aquifer. Okay, let's say we bring this is confined aquifer, and we take the small cube of the porous media, or cube of the sand. Okay, the sand is the size of this is dx, dy, dz. Okay, and we put in the rectangular coordinate x, y, z. Okay, for explain the flow. So it means this flow can passing through three directions. Okay, we start from the x direction first. If the flow start from this Vx, and one is passing through this left flow out on the right hand side. So this is cancel this no, it should be, so it means the change of velocity can be delta Vx. So this is a change of velocity. Okay, and this term can be substituted on this, right, in terms of the differential, partial differential form. Okay. Can use the same color. Okay, so it means the change of the velocity. So in this case, if we start from qx is passing through the x direction, and this q we can substitute with vx times ax. Q equal to v times a, and this ax is equal to see that this one, the direction ax is, this is area, dy, don't know, sum from get dy, and from this is dz. So area can be dy, dz. Okay. Then in terms of mass if flow in the x direction is, if we take from the qx, so qx is mean cubic meter per second. So we want to convert from cubic meter per second to mass. So we have to multiply by density. So density is mean the unit is kilogram per cubic meter. Okay, you can see that this one we will cancel, and we have to multiply by delta t. Okay, if multiply by delta t again, so s is cancelled, so we got the unit of kilogram, the mass. Okay. If we substitute q in this equation, q is equal to vx ax, and substitute dx is equal to dy, dz, and dt. Okay, so it's mean equivalent to this. That's where it comes from for this equation. Okay, so we can do the same for the x direction and y direction and z direction to derive the mass in for this equation. And for the mass out, it just we have to add the change of velocity in this term. This term is change velocity. Okay, add to all direction. Okay, and we make the difference between m in and m out, so we got this equation. And for delta m, so you have to apply this equation. This is conservation of mass. So we just finished the left hand side, m in subtract m out, so we got this equation. m in subtract m out. Then the next we have to find what is delta m. So we can use the definition of the specific storage. S sub s is from the volume of the it should be okay, should not be lost, is volume, so we so it means the volume of the water, if we use the release form, the storage divided by volume of aquifer and divided by the chain of haze. So based on this, we can derive the equation of delta m. This is equation for delta m based on the definition of the specific storage. Okay, so make the equation 11.7 and 0.8 equal. Okay, so we got this equation, and we do cancel the term that is the same on the left and right hand side. Okay, we got this equation, and the next we have to combine with the Darcy velocity by substitute Vx, Vy, Vz in this equation, and finally we got this equation. It's like the second derivative of the h. In this we can solve this equation using the numerical method. For example, the finite difference method. Given the we call the initial condition and two boundary conditions, so we can solve this equation. Like hydraulic haze is a function of the x, y, z, and t. To generalize problem in to solve the groundwater flow equation, we can assume that for the aquifer is mean isotopic, so it means it doesn't change with the direction, and homogeneous, so it doesn't change with in space. So all k is equal, is constant in space. So we can get this equation. Okay. And the second derivative of the hydraulic haze respect to x squared, y squared, z squared, and on the right hand side is the unsteady term. If we assume this is steady term is steady state, so it means the right hand side is 0. So we got this equation we call the Laplace equation. And if we assume it's 2 dimensions, so we have just x and z on y is cancelled. And in this case, if we assume the flow in in just one direction, okay, just one direction, so we have only one term. The chain of hydraulic haze, the second derivative of haze respect to x squared, so we can do integration 2 times to get the 2 constant, so we get C1, and C2, and with the initial condition x it means x, when x is 0, h equal to h naught, and we can estimate, and using the Darcy we can estimate C1 and C2, and finally we got the equation of hydraulic haze is a function of the x. Okay, this is equation to explain this equation, this line. So it's a linear in a curve. Slope of the curve is A is equal to B over K. Okay,